Welcome back to Physics 30. This is the new unit, CO2. So conservation laws continuing on. Here we look at analyzing the motion of objects and interactions between objects using momentum concepts, including the conservation of momentum. So this video we'll look at the first part here, 2.1 momentum and its relation to force. Then we'll look at conservation of momentum, then collisions and impulse, conservation of energy and momentum in collisions, elastic collisions, and inelastic collisions. So in this first one, 2.1 momentum and its relation to force, we'll define linear, so moving along one line, momentum, and write the mathematical formula for linear momentum from memory. Distinguish between the unit of force and momentum, write Newton's second law in terms of momentum, because that's how it was originally defined, and solve problems involving momentum. So linear momentum, or simply momentum for short, of an object is defined as the product of mass and velocity. So plural is momenta, is represented by the symbol P with the vector over top, because it is a vector. If we let M represent the mass and V velocity, it's just simply this. You can think of it as the amount of oomph an object has. So if an object has a large mass and a small velocity, it has a lot of momentum, like a slow-moving train. If something has a small mass but a really large velocity, such as a fired bullet, it has a lot of momentum. If something has a big mass and velocity, then it has a really big momentum. So I like to think of it as the amount of oomph an object has, dependent upon how big it is, its mass, and how fast it's moving. So since velocity is a vector, momentum is too, so the direction that velocity has is the same as direction of momentum. The direction of the momentum is the direction of the velocity, and the magnitude is simply mass times v. Because velocity depends on the reference frame, so does momentum. Thus, reference must be specified, so north, south, etc. The unit for momentum is that of mass times velocity, so mass is kgs, velocity is meters per second, so kilogram meters per second. Quite often when we have a weird unit like that, we have a special name for it or a derived unit, but in this case we don't. It's just simply kilogram meters per second. Everyday usage of momentum, everyday man on the street description of momentum is similar to what we have here, the amount of oomph. A fast-moving car has more momentum than a slow-moving car of the same mass. A heavy truck has more momentum than a small-moving car with the same speed. The more momentum an object has, the harder it is to stop and the greater effect it will have on another object if it's brought to rest by striking that object. A football player is more likely to be stunned if tackled by a heavy opponent running at top speed than by a lighter or slower-moving tackle. A heavy, fast-moving truck can do more damage than a slow-moving motorcycle. Over here, can a small sports car ever have the same momentum as a large SUV with 3 times the mass? Explain. And of course, yes, it can. Because momentum equals mass times v, so I can't change the mass of the sports car, but I can sure change how quick I'm moving. So if the velocity increases. Now these are all direct relationships here, directly related to m, directly related to v. So if I can increase the velocity by 3 times, I'll have the same momentum as that heavier SUV, which is much more massive. Next page. A force is required to change the momentum of an object, whether to increase the momentum, to decrease it, or to change its direction. Newton originally stated his second law in terms of momentum, although he called the product of mv the quantity of motion. So I called it the oomph, Newton called it the quantity of motion. Newton's statement of the second law of motion, translated to modern language, would be the rate of change in momentum of an object is equal to the net force applied to it. Or we can write this as change in momentum per time, the rate at what change in momentum is equal to force, now that's the Greek symbol sigma, meaning the sum of, or the net force, where the net force applied to an object and delta p of the resulting momentum change that occurs during the time interval t. Okay, so if we look at how that applies, so net force applied, delta p is change, so we can really derive F net equals ma, which is Newton's second law that we took in FM2 from the equation above. So if I look over here, so if momentum is equal to mass times velocity, then change in momentum is equal to mass times change in velocity. So if the force applied on an object is equal to the change in momentum that that object experiences per time, take a look at what happens here. So delta P can be represented as m delta V. And of course, m delta V is the same thing as the delta V part, V final minus V initial. And of course, if I apply m across to both of those, it's mv final minus mv initial, or mv2, mv1. It doesn't matter. Final is 2, initial is 1, etc. Or if you take a look at it, if I go back a step and write this back as v final minus v initial, or v2 minus v1, that's the same thing as delta v. And yeah, change in v over change in t is acceleration. So F net equals ma, where delta v multiplied by m is change in momentum. So that's originally how Newton's second law was defined in terms of momentum. And of course, we back in FM2, we looked at it as simply mass times acceleration. So the F equals delta P over delta T equation is a more general statement of Newton's second law than the more familiar F net equals ma, because it includes a situation in which the mass may change. Change in mass occurs in certain circumstances, such as rockets, as they're expelling fuel, their mass, of course, changes. All right, we'll look at an example here, an easy one with momentum. For a top player, a tennis ball may leave the racket on the serve with a speed of 55 meters per second. So if you imagine you're hitting a tennis ball, originally it would be 0, and then leaves the racket at 55 meters per second. If the ball has a mass of 0.0 kgs and is in contact with the ball for 4 milliseconds, which is 4 times 10 to the minus 3 seconds, estimate the average force on the ball. So we have some room on the next page here. So we know we're looking for F. We know 2 velocities here, initial and final, etc. So we could, F is equal to, so the average force on the ball is equal to change in momentum over time. Change in momentum, of course, is m delta V over T. And of course, delta V is really V final minus V initial over time. Oops. And of course, I could apply the m across to both. Doesn't matter. There's a couple of different ways you can handle that. So the mass of the ball is 0.060. The speed that the ball leaves with is 55. Initial was 0, and we're told that this all had 4 times 10 to the minus 3 seconds. So that works out to be 825 newtons, and I think 2 sig figs here throughout, so I'll round it off to 2 sig figs. All right, so you should be able to do the assignment. The assignment deals with Newton's second law here. It also just deals with simply calculating momentum. Momentum is equal to mass times velocity, or you could figure out change in momentum, in which we have 2 velocities, and then of course we have this relationship here. The forces involved is when the rate of change of momentum happens. So the assignment kind of looks at all of those. All right, so you should do okay with that. See you again.